the first one, terms. So you might have learned this in lecture. So what is valence electrons? Valence electrons is, I hope you guys can see, is the electrons. So I'm going to use E minus because electrons take negatively charged, right? So I'm going to use E minus as electrons. So it's the electrons in outer shells, okay? So what does it mean? For example, in carbon, so let's go to the periodic table a little bit. So carbon has 6, nitrogen has 7, oxygen has 8. So let's say if we go to carbon that has 6, so that's a review of Chem 2. So that's SP. So this one is for the outer shell. There are 4 electrons in the outer shell. So there are 4 electrons, 4 valence electrons. So similar things to oxygen. Oxygen has 6. If you do that, oxygen is positive 8. So it's 2, 6. So this one. So it's this one, okay? And the nitrogen has 5. The second thing is what is ionic and covalent bonds. I think I was listening to the video of Sarah Levis of Tuesday, her lecture in Tuesday. She talked about this. So I actually just print them here. So ionic bonds is the bonds between 2 ions. When we talk about ions, that means we have a formal charges. What do I mean by formal charges? It's either going to be positive or something like, for example, negative. So they are formal charges. Where if it's covalent bonds, it's sharing of the electrons, which means, for example, my carbon. So each one donates 1 electron. So they are sharing the electrons. So it's not a formal positive or formal negative. Well, let's say make this one into oxygen. Then this one is going to be partial positive, partial negative, because oxygen is more electronegative than carbon. Okay, so what else? Making bonds. So 8 electrons, so that's the Octet rules, just a recall for that. This one, there's a double bond. See, there's a double bond. There's a triple bond. So that's YNE, ENE, ANE for single bond. Calculus structure is always going to look like this. It's 90 degrees to each other. Although it might not be exactly the same thing in reality, but you should be able to condense them, which this CH3 corresponds to this part, and this part is CH2, and this part is CH3. So you should be able to condense them into the most simplified way, which is also the practice. The CH3NO2, that's aniline. So structure, we also write in the way of bond line. So each end carbon is each end is a carbon. So there are 3 carbon here. That's I highlight them with red. So each carbon is an end. We don't write the hydrogens on carbon. But if it's something else, for example, if I change this one into chloro, then you need to draw that chloro out because it's no longer a hydrogen. So if I'm changing this hydrogen into OH, so OH, do I have to draw the H out? Yes, you have to. So the OH should be like this, HO. Wedge dash, wedge means out, dash means in. If I want to make the chloro out, it will look like this. The hydrogen is dash in, for example. So keep in mind when we are drawing wedge dash structure, first, each carbon only has 4 bonds, and it's always going to look like 2 solid, 1 dash, and 1 wedge out. So that's just keep in mind. You need to check each carbon. Question: how do you know which is in or out? We will give you a wedge dash structure, and as long as you can recognize the wedge one is out, the wedge chloro is out. For example, in our case, and the dash one is in, that should be fine. There's another question. Let me see. So we wouldn't need to know whether or not chloral is out or in. Yes. So basically, this chloral can be out, can be in. So there are many ways to draw this structure. I think in week 4 that you are going to learn R and S. That's where those things matters. For this week, you are only expect to know that if I have a structure that is has chloral here and a hydrogen here, these are 2 different structures because in one of the structure chloral is wedged out and in the other structure chloral is dashed in. The black one in the middle is the center carbon that we are talking about. So when we are talking about wedge dash, the yellow atom is in front of the paper, where in the other side of the paper, there is another one. So that's what we mean by dash in and wedge out. So that's in a plane that my hand is in. And on the plane of my hand, there's a gray atom and a black atom. So these 2 are on the same plane. Well, the yellow one is out, and this black one with a hydrogen is in. So I just want you guys to know for now that if I am change this one. So for example, if the yellow one is the chloral, if I'm change the yellow one into the back, this is different from what it was before. So this is more like the expectation in week 4, not now. So don't worry about that. I just want you guys to know there is a wedge and dash in a way that we are trying to describe structure. Alkene, the condensed structure for this. So let's just count. So this one, I'll go to blue. This one is CH3, and there's only CH. See, there's only 1 hydrogen, so it's CH. You don't have to write CH1. It's just CH. CH, CH, CH3, right? So alkyne, the same thing, but it's going to be CH3, carbon, carbon, CH3. So people is going to ask, how would you know that there is a triple bond? Because there are no hydrogens. We just count for that. Magic code in chemistry, that's only chemistry people know that there is a triple bond. So you start to learn those language. So that's how it works. So alkene, because we talk about if the hydrogen is bonded to carbon, you don't have to show that hydrogen. So each red carbon in the structure that I drew before in the calculus structure is a red point. But when you are writing, you don't have to show it in a different colors. I'm just doing this for instruction. So you should know, although I didn't draw out, there are, I'm going to use green. So there are 3 hydrogen bonding to this carbon. There are 1 hydrogen bonding to this carbon, although I didn't draw out. So you're supposed to know that. How do you know there's 3? Because carbon has 4 bonds. And isn't that structure you draw not chiral, since not all things attached to the center carbon are different? There are 2 hydrogens. Correct, it's not chiral. We will get there in week 4, but that's a good point. So I didn't assign R and S. So keep in mind, this one should be 120 degrees. The things that you should also pay attention to when you are drawing alkyne, I'm still going to highlight the pink carbon. It's 180 degrees. So this is 180 degrees. So while this one is tetrahedral, but I cannot draw it here. Each of them should be 109 degrees. The most common mistake why I see students drawing alkynes, they are trying to draw in a way that's like this. So this is not correct. So don't draw it in a way like that. So hydrogen wedge out, dash in. It won't really matter about that. So the same for alkyne. I'll just you can draw them by yourself. But nitrogen, I've seen most students struggle on that because usually nitrogen looks like this. So nitrogen is comfortable with a lone pair and 3 bonds to something else. So let's say R1, R2, R3. So in organic chemistry, R means CNHN, which means there are only carbon and hydrogen. You don't have to show what it is. So that's another magic code in organic chemistry. So let's say nitrogen is most comfortable with the structure like this, but it can show positive charge if if nitrogen donates its one of electron out and form a bond. So if it donates that thing out, so nitrogen can also be R4. So in which case one of the electrons, so these are the two. So these are the two that's the lone pair, but nitrogen donates one of its electron in lone pair out. So nitrogen is going to form a positive charge if it looks like this. Like someone grab this R3, I don't know what the R3 is, and these electrons go back to the nitrogen. R3 donates its nitrogen here. So nitrogen can be negatively charged. So it's all about nitrogen has 5 valence electrons, but how to understand that is if it's 5, it's neutral. If it's 6, so 1, so see how many, let's count. So 1, 2, 3, 4, 5, 6. If 6 is negative, if there's only 4, 1, 2, 3, 4 is positive. Only if it's 5, then it's neutral. So that's why you need to record that we need to review on nitrogen has 5 valence electrons. So oxygen has 6 valence electrons. So let's say you will see OH a lot, especially if you are going to use alcohol. So that's how it works. But in oxygen, that's the 1, 2 in 1, 2, 3, 4, 5, 6. So oxygen is neutral if it's in this way. Okay, so let's make them smaller. And you will be able to see positively charged oxygen like this. So you might see a positive charge like that in a way that a base is grab the hydrogen and transfer the electrons. So this is this. So that's the neutral, negative, and positive charge for oxygen. So think about what we just talked about. Nitrogen needs 5 valence electrons. Let's just put the sigma bond between nitrogen and oxygen in. And how about oxygen? Okay, so nitrogen has a positive charge with the 4 bonds here. And oxygen, I'm going to use another color. Oxygen, overall is neutral, but actually one of them is positive and the other is negative. So the total charge for the structure is neutral. You won't see that much things like NO2s in your exercise or quiz. And what is CO then? So first I know there is a carbon bonded to this carbon. And now I know C needs to have a bond with oxygen somehow. Let's say put the oxygen here. And then there's an NH2. So that's actually easy. So keep in mind, nitrogen is most comfortable with 1 pair of non-pair and bonded to 3 other things. So this, I know this nitrogen is going to be neutral anyway, right? So I'm done with this part. But how about carbon and oxygen? So carbon and oxygen. Carbon needs another bond, and oxygen is only bonded to one thing. So according to what we learned before, that's if oxygen is only bonded to one thing, it should be negatively charged. But now I don't want that to be happen. So I need a double bond here. So carbon is happy because it has 4 bonds. Oxygen is happy because it has 2 bonds. And oxygen also has the other 2 lone pair. Here, CHO. So I will just ignore the CH2 CH3 because I think that's too easy. So CH3 CH2. Let's say so CHO. So this is aldehyde actually. the things that I'm putting in a red square now are some of the structure that you can work on with, or I would just recommend you to remember them. How does your light blue check mean? My light blue check means I check the structure. I know I'm done with that nitrogen. The nitrogen is comfortable. So sorry that I didn't read that. So the way that when I'm drawing structure like this, I like to check if I'm done with that nitrogen. If I'm done, I've counted the electrons on my nitrogen and the charges appear to be good, then I'll check them. So the same thing, if I have to check all of my atoms, then it's done. But you don't have to show the check when you are in exam. In the second dash structure, why did you only draw the hydrogens on the right side? Oh, because I only want to show an example of this. So if you want me to draw them out, it should be hydrogen, hydrogen, and dash hydrogen, wedge dash solid hydrogen. When you write the condensed structure, you write hydrogen first after carbon, then everything else after hydrogen is alphabetical order. Yeah, correct. So the way that I want to teach how to draw resonance structure is you should know resonance is electrons that move. And where should I start to draw a resonance structure? You should start to draw resonance structure by searching in your moleculars. That's if there are any p orbitals. So p orbitals means the fourth thing here. So means high long pair. Oh, there's a typo. PAIR, long pair electrons. For example, the oxygen one that we talk about. So you don't have to form. So this long pairs, you don't have to form a formal negative charge to start the resonance, as long as you have long pairs. So of course, electrons in double bond, let's say CC, yes, you can start to do resonance structure like this, something else like that. And of course, if you have double bond, you should be able to have triple bond, well, in the way that you want. And a formal negatively charged. Usually when you have a formal negatively charged, it means you will have a bunch of non-pairs. So what are the other formal negatively charged? Like this, right? So long pair electrons also includes coral, like this. So, but you might not be able to see the a resonance on coral very much, because coral is very electronegative. Well, that's something else. I'm just trying to show you where should you start. So when you first guess the question like this, we might not be able to show you all the long pairs just for the easy, because we know they're long pairs. But you should draw the long pair if you want to see where should I get started. I have drawn out the resonance format here. So pay attention to the arrow. You only use this arrow in resonance and with a record on both sides. This is the only place you use this record. If you are going to write a reaction, it's one end arrow, not double end. So this is the only place in organic chemistry that you're going to use this arrow and use it correctly. So for example, benzene, let's say benzene has double bond, right? And let's say when we go to find where should we start, is the electrons in double bond. Nice. Then draw the arrow starts from where the bond, where originally the electron is. And push the electrons. Oh, you're confused. I'm sorry. I'll redraw this again. So originally, each carbon has a p orbital, which is the electrons. And I was forming a double bond like this before. Now I'm just trying to form double bond like this. Is this way clear? Okay. So originally it looks like this. So that's why I push the electron to this side, and to this side. So think about the most comfortable ways. Think about the ways that we talk about. Nitrogen is most comfortable with long pair and 3 bonds, right? So what else nitrogens can have? If it's 4 bonds, it's positively charged. If it's 2 bonds, it's negatively charged, right? That's a quick review. Oxygen. So oxygen is neutral now, and oxygen is positively charged with 1 pair of lone pair, and oxygen is negatively charged if it's bound to one thing. So just keep in mind of that. So what are the things that we can do here? So the electron, the red electron that I'm highlighting here, is going to move to here and form a double bond here with the carbon and the nitrogen, right? And then this carbon is not going to be happy because this carbon is going to have 1, 2, 3, 4, 5 bonds. So it's going to push its double bond onto oxygen. So that's what is happening here. That's when we draw resonance structures, we draw something like this. Starts with the lone pair. Don't start with the atom. And then push the electrons from carbon and oxygen to oxygen. So originally oxygen has 1, 2, 3, 4. Originally nitrogen has that, right? So the green one, I'm leaving this one green because that's actually the only electrons that move. So if we're doing this, I'm going to leave this page like this, okay? So first, I'm going to form a new bond between nitrogen and carbon. Second, oxygen, 1, 2, 3, 4. And then there are 2 lone pair, there's a pair of lone pair. So actually one of them originally is itself. The other, so the one that is moving, let me just use another column. The one that is moving, the one that is moving is the one here, okay? The one that is moving is the one here. So it's the yellow one that is moving. Originally, this yellow one was the electron from the carbon. And then it's going to form a negative charge. Here, the nitrogen, since it's losing that, so it's going to form a positive charge. So that's how the resonance structure is. And see, if you are familiar enough with what we talk about, how a positive nitrogen and how a negative nitrogen look like, you should be familiar with this. And then say, I think if I can get a negative oxygen and a positive nitrogen, that should work. Why isn't there a resonance structure with a carbon cation, carbon with a positive charge, and the negative charges on the oxygen? You can, yes. So I was just drawing one way of the resonance structure here. You can have more than this. If you don't want to start with the lone pair here, you want to start with the double bond here, then you can do a resonance structure like this. Then it's going to be positively charged carbon and the negatively charged oxygen. And you can keep moving because there is a pair of lone pair on nitrogen that is going to fill into the position of your positively charged. Then it's going to go to the one that we draw. So there are many resonance structures that we can draw as long as it's correct. What do I mean by correct? It means each atom is taking the correct number of electrons. Each atom has been assigned to the correct charges. And it's reasonable. Then that's fine. How about I'll give you a few seconds to do the resonance structure like this. I didn't draw the oxygen out because I want you to draw it. And we're going to draw them together. So there are plenty of things that I can get started with my resonance structure here. For example, there are double bond between carbon-carbon. There are double bond between carbon and oxygen. either of them work. You can draw a bunch of resonance structure here. For example, if I just want to do the same thing before, then this would be a resonance structure like this. And I might just want to start with this one. So, and this would be a positive charge here, oxygen minus and a positive. Can the oxygen atom move too? What do you mean by move? Do you mean you want the, so when we talk about resonance structure, we don't move any atom. We only move the electrons on atom. So you should always keep in mind, if you want to move any atom, no, I don't think that's really possible. So the way you can, the atom stay in the same position as it is. The only thing that you are change in resonance is how it bonds to other atoms. Oh, there's a question. Why is the positive charge not on a carbon with only 3 bonds? Previously, this carbon looks like this, hydrogen, hydrogen. So now I'm breaking this bond. So previously it looks like this. Now I'm moving this electron into here. So it's forming a bond with this double bond. So the carbon that is losing a positive charge is going to show positive. Does that answer your question? So let's come back to here. So structures, resonance structures are a mixture of depictions, which means it's like the person that you're taking photo of a person, but this person might wear in different poses. So for example, the 1, 2, 3 structures, if I'm taking 10 photos for the same molecules, I might see structure 1 or 2 or 3. It all happens. It's just a matter of which one is dominant. So that's come to our second structure. So not all structures are equivalent. What does it mean? So here, this is going to be the major structure because it doesn't have a charge. So it's neutralized to itself. It's the most comfortable way. And usually the structure that's with less charges, separation, like this. So you have a negative and you have a positive. This structure is not going to be as comfortable as the one that's everyone just take its own electrons. I'm not borrowing money from others, and I don't own someone money. So that's kind of in the most comfortable way that each atom is. So this is going to be the major structure, and this is going to be the minor. The same one here, the minor. So, but it's not always going to be the same case. We're going to talk about an exception next week. There is a structure that's with charge separation that is actually the major structure of all its resonance. But for now, you just need to keep in mind, usually the major resonance structure is the one that has less charge separation. This is the end of our notes. So I was a 118 student, which means I took the whole series in UC Davis. I was in your shoes like 5 years ago. Oh, it has been 5 years. That's too long. I kind of know where your problem is. And then I'm trying to help you in a way that I think it works for me. Once we start to go to week 6, which is you start to learn SN2, SN1, E2, E1. Those things are mechanisms. So you will see this word, mechanism. And I recommend students to do flashcards on them because that's the way that it works for me. So for each mechanism, for each reaction with mechanism, I'm making a flashcard. I think I still have them here. So this is the mechanism flashcard that I was using when I was in 118. I didn't know this method until 118B. So you will be, so I'm just showing several of my flashcards here. That's on each flashcard, there's a reaction and there's a mechanism. And some of the mechanism is going to be very complicated that I cannot finish in one page. And for each reaction, I'm doing this. So I would recommend you guys to start doing that. Once you start to learn the first reaction with mechanism, I number them in my 118A, and I think there are totally 17. there are totally 45 reaction that you have to memorize its mechanism. So 45 in 118B, 17 in 118A. So go find those 17 and make flashcards with them. After I've done a bunch of flashcards like this, like that's the reaction and the name and what's the chapter and what's the number, and you start to do a bunch of mechanisms like this, you are going to use those flashcards as bridge. Because once you start to learn stuff, like alkyl halides is chapter 6. So this is chapter 6. And 6 and 7, actually. Alcohol, I believe, is chapter 8. And ether is chapter 9. That's, if you don't know what I'm talking about, you just can think about each chapter as a city. We are responsible to teach you, yes, you can make alcohol from holoalkane, or you can make alcohol you can use alcohol to make ether into the chapter 9. But it's your responsibility to link them together. This is a reaction. Let's say, actually, if I'm going to fill in that now, the condition should be acid. So I'm going to use acid to go back. So how should I go from alcohol to ether? Then you can, well, there are many other ways, but let's talk about, so you just fill in the map by checking your flashcards. So this is the way that I think is going to help you, because you are going to see a bunch of synthesis, which is the words that's what we are using for making things in organic. I think I have a empty reaction map. That's the exact reaction map that I was using in 118A. So you can go ahead to make your own, because I think each of my students has different reaction map. As long as it's clear and it's correct, it's useful. Another thing that I think is going to be very helpful is a table like this. It's going to talk about the pKa and the functional name. So you will be able to get this help sheets by searching UCD SASC. I think Sarah Levens also listed this one in her syllabus. So you just search UCD SASC, you should be able to find this one. So that's the end of this discussion. Okay, so we will see you guys a while in office hour. Thank you guys, bye.